Well, welcome to my talk on the use of data science and Earth observation for spatial decision making. And now, before carrying on, I'll make a basic assumption, and that is that all or most of you in the room want to know about if and how spatial or locational data improve decision making. And actually, spatial data have been informing decision making since antiquity. Now, this is a map which shows the geolocations of the cholera outbreaks that occurred in London in 1854. That was in the 19th century, a very long time ago. And the map was created by John Snow, and the red dots are where the cholera cases were reported. And this was one of the first few maps of its kind where the outbreak of a disease was actually plotted using spatial data. And therefore, John Snow is credited with the founding of both spatial analysis and modern epidemiology. But in the modern days, spatial data, they do find a lot of use in mapping and evaluating the spatial distribution of voting patterns. So on the left-hand side, you have the map of the different counties in California, and these have different shades of blues. And the different shades of blues indicate the proportion of yes votes that a topic received across the different counties in California. So the darker colors represent a higher proportion of yes votes. A more famous example is on the left-hand side, a map that no one's going to forget in a hurry for many years. And the map comes from BBC News, and this is the percentage leave vote per constituency in the EU referendum 2016. And the darker blue colors, they represent a greater percentage of the voters in the constituency voted to leave the EU. And now with this, you can actually see how the leave vote was distributed throughout the country. So there are places, especially in the far east of England, where it would seem that more than 70% of the electorate voted out, and there are parts in the northern parts of the United Kingdom where less than 30% of the electorate voted out. And now another interesting use of spatial data has emerged in the field of Twitter or social media mining, where we can visualize the geolocations of tweets or Facebook posts pertaining to a topic. So now this is one example. You can see the spatial distribution of tweets with the hashtag Jerusalem Embassy. And just to give you a brief background, on December 6th, 2017, US declared Jerusalem as Israel's capital, and within minutes, Twitter was awash with tweets containing the hashtag Jerusalem Embassy. On that day itself, I mined about 10,000 tweets, and I visualized the geolocations of the tweets. And the initial tweets, or the initial 10,000 tweets, they mostly came from the United States, especially the eastern coast, a lot of them from the western coast, from the United Kingdom, and quite a few tweets came from India. And essentially, quite rapidly, I could see where exactly was this particular hashtag making an impact. Okay, that's just about it. Now you must be wondering, is spatial data all about visualizing geographic data? And yes, for a very long time, arguably, spatial data were mostly about visualizing geographic data. And in normal course of events, my experimentations with tweet mining should end here. I have a map which tells me where the impact of this news was most felt, but that's not the case. And in that comes data science, and data science helps derive valuable insights from spatial data. So we no longer need to just stop at visualizing the geographic data. We go much, much beyond that. So carrying on with the tweets that I harvested off Twitter, I analyzed the sentiments behind the tweets with the hashtag Jerusalem Embassy. I did so using a data science technique known as natural language processing, which enabled me to quantify the dominant sentiments underpinning all the tweets. And it would seem that the initial tweets or the initial tweet, 10,000 odd tweets, were mostly positive. But of course, we can literally drill deeper and see how the sentiments may vary across regions and demographic groups. And this is the kind of power that we get from data science. Now, the rest of my talk will be devoted to helping you understand how spatial data, including something known as Earth observation data and data science techniques, can inform and even improve decision making. But first, who of all the people am I to talk about spatial data and data science? I have been introduced previously, so just to quickly reiterate, I'm Minerva. I'm a PhD graduate in tropical ecology from Cambridge. I have an MPhil in environmental sciences from Oxford and several years of experience applying machine learning techniques to both remote sensing and spatial data. I'm also an edupreneur with udemy.com, and I'll be joining Imperial College as a research fellow in a few days' time. And the most important thing is that I want to unpack what is spatial decision making, and I'm not going to jargonize you with definitions and things. Let's just try to understand it in a very intuitive way. So the way I see spatial decision making is that this is a form of decision making that involves the use of spatial and geographic data. It can include anything, starting from the top left, establishment of protected areas, to hydrological applications, to even the hiking GPS units. So when we go out for things like hiking, cycling, or driving, we have GPS units. And when we walk or cycle wherever we go to, that is a form of spatial decision making. And even buying and renting a house is a form of spatial decision making, because apart from the price, we also take into account the spatial factors such as distance from the bus stop. And now, spatial data analysis also includes something known as Earth observation data. Earth observation and remote sensing data, these are terms that may be used interchangeably, and remote sensing data are acquired for an object, example, a landscape or phenomenon, without any direct physical contact. So most of you can see me standing up here, and you can see I'm wearing a yellow dress, and that is a form of remote sensing, because you've seen me, and without any physical contact, you know I'm wearing a yellow dress. Now, the conventional remote sensing data, they are collected using either satellites or aircrafts, and on the top right corner, you can see an Earth orbiting satellite, and these are the satellites which are used for collecting Earth observation or remote sensing data. Landsat satellites have been functional since the 1970s, and they were launched by the United States Geological Survey. Landsat data have a spatial resolution of 30 meters, which means each pixel and every image that you work with, including the photos that we take on our smartphones, comprise of pixels, which is the square area of an image, and 30 meters means that the sensors can resolve objects as large as 30 meters on the ground. And on the bottom right corner, you can see the Landsat view of Tasmania. And the different colors, they are influenced by the different features present on the ground, including things like vegetation. Darker green colors mean darker vegetation, and so on. Additionally, the governments of Japan, India, and Canada have also launched their satellites which provide Earth observation data. In addition to satellite data, we have something known as high-resolution Earth observation data. They comprise of things like LiDAR data. LiDAR data are data which are collected typically through aircrafts or helicopters, and they use lasers to capture the 3D object structure. So you can see LiDAR data collection on the left-hand side, where a laser beam is beamed onto a surface, and when these laser beams are reflected back, the reflected lasers, they give us an estimate of the object structure, things like tree heights. And on the right-hand side, you have a classical example of high-resolution aerial imagery. These are typically of spatial resolution 1 meter or below, and they're collected using airplanes or drones. And what you can see is the aerial view of Angkor Thom of the Angkor Archaeological Park in Cambodia. And you can see the minutest details quite clearly, including right in the center, we have something known as Bayon, a very important temple in Cambodia, and you can even make out the individual tree canopies, etc. So, how do data science techniques, things like machine learning, come into the picture? But just to briefly iterate what I mean by machine learning, or just to give you a definition, these are computational algorithms that use statistical techniques to allow systems to learn from data in order to build predictive models. So we typically have data from different sources, source 1, source 2, source n, which are cleaned and transformed into features or predictors, which is fed into a machine learning system in order to build predictive models. Machine learning and remote sensing make very good friends, and that is because remote sensing data usually comprise of multiple bands that are inherently nonlinear. So on the top right corner, you can see a stack of remote sensing bands. These are hyperspectral imagery, but these are the kind of data we get a lot with Earth observation collection. On top of that, many physical properties, example, forest types, can be spectrally similar and therefore difficult to resolve using ordinary statistics. So on the bottom right corner, we have the spectral signatures of different forest types in Cambodia, and you have things like cashew forests, degraded forests, and so on. And while all of these have their own signatures, but these signatures are quite close to each other, so resolving them becomes difficult. And when we have a tremendous amount of optical data, the way we have in the top right image, we get something known as curse of dimensionality. So too much data becomes a hindrance than a help. So in this situation, machine learning algorithms are universal approximators, and which means that they learn the underlying behavior of a system. They are not influenced by data distributions, and data distributions are an important consideration as far as parametric statistics are concerned. And with machine learning, we don't have to worry about that. So machine learning data are used in conjunction. Machine learning is used in conjunction with remote sensing to produce predictive maps of continuous properties, such as forest carbon using regression or land cover classification using classification methods. So does the marriage between Earth observation data and data science actually inform decision making? Okay, this is a tough question. It's likely to vary across your disciplines. So I'll just provide you with a few examples from my own PhD. So on the left-hand side, we have the 3D structure of a woodland in Cambodia. This 3D structure was obtained using LiDAR data. So once we had an estimate of the 3D structure of the forests, we fed it into a machine learning algorithm to obtain forest carbon estimates. And on the right-hand side, we used multiple Earth observation data streams, data from optical sources, LiDAR, radar, to build a map of suitable habitats for endangered birds. So darker areas, they represent suitable habitats for birds. Machine learning has been extensively used. Machine learning models have been used a lot for remote sensing-based mapping. So carrying on from the previous example, on the left-hand side, we have the forest carbon distribution of the woodlands in Angkor Thom. We obtained it using a machine learning technique known as random forests, and essentially, so the estimates of canopy heights were obtained using Earth observation data, and that became the basis of being fed into the algorithm to obtain this map, and it helps us identify the areas where we have high carbon storage, low carbon storage, and so on. On the right-hand side, I have the land cover mapping of a study area in Cambodia done with Landsat, and again, Landsat data were fed into a machine learning classification algorithm to map different forest types, and now we can actually, on the ground, evaluate and map the spatial distribution of different forest types and their concentration. Now, if you are to carry out any spatial decision making, you'll find yourself working with geographic information systems as well, and they are not to be confused with Earth observation or machine learning, because geographic GIS offers a way of using the insights from remote sensing data for informing spatial decision making. Now, the role of GIS can range from building maps. So on the left-hand side, there's a GIS derived map of a study area in Kalimantan, Indonesian Borneo, and a map like this is typically used to carry out field work. And on the right-hand side, we have an example of where GIS was used within spatial decision making. So different layers, including Earth observation layers, were fed into a GIS system, and where GIS operations such as buffer analyses, union was carried out, and the computations in turn helped inform decisions on urban land suitability. In a nutshell, based on my experience, these are the different steps needed for spatial decision making. So you have the first thing that you have on the top left are field collected data or input data. These can be anything from geolocations of birds, the way I collected them in Cambodia, to say district level poverty estimates a colleague collected in Thailand, that we combine with remote sensing data, example something like Landsat or radar or a combination. We apply a machine learning algorithm, something like random forests, support vector machines, and obtain mapped outputs, example something like a habitat suitability map that you saw before. And now it's perfectly okay to terminate at this step, and you need not go further. And there are many papers which simply obtain a mapped output and that's that. But in some situations, you may want to apply GIS tools and techniques to facilitate decision making or inform planning. And I'm going to give an example of how I use GIS tools on my mapped outputs to help policymakers in the Philippines. So we use GIS for deriving actionable insights from machine learning-based predictions. And we carried out the research in Palawan, an island in southern Philippines. And again, machine learning techniques were implemented on a combination of Landsat data and radar data to map the distribution of forest carbon, and we obtained mapped estimates of bird species richness. So just to go back, we managed to get up to the part pertaining to mapped outputs using machine learning. And yes, I could have stopped at that point, but that's not what we did, because we needed to drill deeper. So geographic information system based approaches were used for identifying statistically significant areas of high carbon and high bird richness. These are known as hotspots, and spatial statistics techniques were applied to identify areas where you had a statistically significant high concentration of something like forest carbon and statistically significant low concentration of carbon and birds. So on the bottom right, you have the map that we obtained, a map of hotspots in red and the map of cold spots in blue. So the hotspots tell us that these are areas where you have significant amounts of carbon deposits or significant amounts of endangered birds. So even if you don't, I don't know how many of you are ecologists, but that's besides the point. You just have to look at a map like this, and now you'll know right away, which areas to prioritize for conservation and which areas can be left out. And these are the kind of actionable insights that we can derive using GIS techniques. After that comes something that we discuss a lot, and I hope to use this in my future research, and that is neural networks and deep learning for spatial decision making. So maybe by next year, I should have more information on this topic. But right now, let us just see how do machine learning, artificial intelligence, and deep learning tie in. So artificial intelligence is quite a huge area. It has been in existence since the 1950s. Machine learning is a subset of that, and deep learning it falls within the family of machine learning. There are many people who insist that deep learning is a different kettle of fish, but that's a matter of argument. But what deep learning does is that it aims to mimic the activity in the neurons of the thinking part of the brain. So on the right-hand side, we have this figure by Andrew Ng, which tells us why do we even need deep learning, because implementing and executing deep learning systems is tiresome, quite tiresome. And that is because as the amounts of data go up, the performance of other conventional machine learning algorithms goes down, but deep learning is well suited to give very good results with a huge amount of data. And an interesting example from my field that was published earlier on in this year, in the proceedings of the National Academy of Sciences, researchers from Harvard, Oxford, and Minnesota, they built a deep learning-based model which helps carry out automated animal identification from camera trap images. So the camera traps, they were put up in the Serengeti National Park in Africa, and a lot of photographs of different animals doing different activities were captured. And usually people have to sit in front of these camera trap images to identify what animal it is and so on. But they built a deep learning model which can do all of this automatically with 96.6% accuracy. They use something known as deep neural networks, which could successfully identify, count, and describe the animals in the camera trap images. So on the top, you have the human-provided inputs, where human beings have identified what the animal is and what it's doing. And then on the bottom, you have what the machine learning or the deep neural networks identified, and they were really quite accurate. So this could potentially save a lot of time and help conservation in the field. Any questions? I mean, thank you for listening, but I'll be happy to take any questions.